Hi, I'd like to talk about shock waves. And shock waves are waves that can be produced in any sort of wave system. The key to having shock waves is an object has to be able to travel faster than the speed of the wave energy in whatever system we're dealing with. So, from our discussion of the Doppler effect, we said if we're traveling slower than the speed of a wave, if we're moving sort of in the direction of that wave energy, then the waves that we produce are going to bunch up in front of us. Behind us, the waves are going to spread out. And on a boat, we'd see the exact same thing. The ripples in front of us, as long as we're moving slowly, get bunched up. Behind us, the ripples spread out. Now, if we were to move at exactly the speed of the wave, we're in for some trouble in the Doppler effect, because we'd be trying to divide by zero, and we can't do that. And even if we were to use a proper version of the Doppler effect for light waves, we would still run into a problem at the point where we could be traveling at the speed of our wave. All of the waves that would ripple off would all be bunching up right where we are. And in boating, that's referred to as a bow wave. And anytime you're traveling at the speed of waves on the water, ripples will build up right at the front of your boat, and if you aren't careful, you could actually get a huge sort of surge of water build up that can flood your boat and potentially swamp it. Now, behind, we just get even farther spacing of those wave fronts. Now, the case of a shock wave happens when an object moves faster than the speed of a wave. So if we were to think of an object producing sound, then at any given point, that object would have a sound wave that ripples outward. So I would have to slightly adjust some of these pieces. This isn't really a proper circle. So my object would have to be traveling so that when it produces a new wave, it's going to be beyond the distance that the wave could have traveled from the previous location. We would end up getting a series of overlapping circles. And you would see a line of, in the case of sound waves, pressure build up along a cone emanating out from our object. And you see this in boating all of the time. Anytime a boat travels faster than the speed of a wave on the surface of water, you create a wake. And the wake cone is a shock cone that's being created. And the steepness of that cone just depends on how fast the object is moving compared to the speed of waves. Now, in setting up this picture, I described it as an object being a source of sound. Here's the neat thing. It doesn't have to be producing a wave per se. Silent objects, like if you were to have the ability to just sprint and in an instant be traveling at 500 meters per second, which is beyond the speed of sound, you would create a shock wave because you are traveling faster than the speed of sound. Any object on the water traveling faster than the speed of water creates a wake. Any object moving through air traveling faster than the speed of sound in air creates a sonic boom or a pressure shock. And any object traveling faster than the speed of light in a material, but slower than the speed of light in a vacuum, which we can't go faster than, creates a shock wave of light. So if you ever wondered what plutonium looked like, if you've seen a piece of grayish metal, you've seen what plutonium looks like. It is just a grayish metal. The reason why that radioactive stuff glows bluish green underwater is because underwater, light travels about 25% more slowly than it does through the air. So as some of those materials and that radioactive material disintegrate, they start out traveling just above the speed of light underwater, but below the speed of light in air. So what you see is this bluish greenish shockwave of light being given off until they slow down to below the speed of light in water. So at what angle are we going to get a shockwave? Well, if I were to take a look at, say, this little Heron's wavelet that I've drawn from my object being at this point here, that sound wave travels to the shock cone a distance equal to the speed of the wave times the amount of time that it's had to travel. My object has traveled along the ground a distance equal to the speed of my object times the amount of time it's had to travel. Those two amounts of time are the same, and the ray here for making the Heron's wavelet is going to be perpendicular to my shock cone. So that means that I have the hypotenuse and opposite side of a right triangle, so the sine of the angle of my shock cone is my opposite side divided by my adjacent side, and the angle of my shock cone is the inverse sine of the speed of a wave divided by the speed of an object. So, if an object is traveling slower than the speed of a wave, it can't create a shock cone, because that's not how shock cones work. But the faster you travel, the closer this inverse sine is going to be taking of an argument of 0, the closer that angle is going to get to 0. Thanks for watching.